For several weeks, astronomers around the world had been waiting for one thing: new information about the mysterious interstellar object known as 3I Atlas. Earth-based telescopes were facing a major problem. The object's position near the Sun made direct observation extremely difficult. Bright solar glare created a natural barrier, leaving many observatories unable to follow its movement clearly. But there was another observer in a very different position. China's Tianwen-1 spacecraft was orbiting Mars, far away from Earth's atmosphere and looking at the solar system from a completely different angle. That unique position potentially gave the spacecraft an opportunity to observe the object during a period when Earth-based instruments were struggling. The reported observations have attracted enormous attention because they appeared to show unusual activity surrounding 3I Atlas. Instead of remaining a simple, faint point of light, the object appeared surrounded by a developing cloud of material. Astronomers studying such objects normally expect dust and gas to become increasingly active as an icy body approaches the Sun. But the reported pattern raised additional questions. The material surrounding the object appeared concentrated rather than completely random. Bright regions, extended structures and jet-like features were reported around the central body. At first, these observations could still fit within the behavior of an active comet. Comets are not perfectly smooth balls of ice. As they approach a star, sunlight heats their surface. Frozen material can turn directly into gas, carrying dust away from the nucleus and producing the familiar coma and tail. However, the interesting part was how the activity appeared to change over time. The brightness of the object reportedly varied instead of remaining constant. Such changes can happen naturally when a comet rotates, because different regions of its surface may release different amounts of gas and dust. That means periodic changes alone do not prove anything extraordinary. But the observations became more interesting when researchers considered the object's overall structure. The central body appeared to remain coherent even while significant material was being released around it. If the activity became intense enough, scientists would normally examine whether the nucleus was breaking apart. Yet there was no obvious catastrophic fragmentation in the reported observations. That created an important scientific question. How could an object produce such prominent structures while apparently maintaining its overall integrity? There are several possible natural explanations. The nucleus could have an unusual distribution of volatile material. It could contain regions that become active only when exposed to sunlight. Its rotation could concentrate material into narrow jets. Or the apparent structures could be affected by viewing geometry and the way dust scatters light. In other words, unusual does not automatically mean artificial. One particularly interesting feature was a dark region visible within the surrounding cloud of material. Such a feature could potentially be caused by differences in density, illumination, dust concentration, or the geometry of the coma. Scientists would need repeated observations from different angles before determining exactly what produced it. Another reported observation involved a change in brightness that appeared to come from the side of the object facing away from the Sun. At first glance, that sounds impossible. But light scattering in a comet's dust cloud can be surprisingly complicated. Particles can reflect sunlight in different directions, while jets can transport material away from the surface and create structures that appear disconnected from the simplest sun-facing pattern. This is why a single unusual image is never enough to overturn established physics. Scientists need multiple observations, independent instruments, and detailed measurements. And that is exactly why an observation from Mars could be so valuable. From Earth, astronomers are limited by the planet's atmosphere, the Sun's glare, and the position of the target in the sky. A spacecraft near Mars experiences a completely different viewing geometry. It can observe the object from an angle that Earth-based telescopes simply cannot reproduce. That means even an ordinary comet can look very different when viewed from another location in the solar system. The real importance of the observations therefore may not be that they prove something mysterious. Their importance could be that they provide another piece of the puzzle. 3I, Atlas is especially valuable because it did not originate in our solar system. Whatever its true nature, material from another planetary system has entered our neighborhood and is now passing through an environment we can study. That makes it a natural laboratory for comparing planetary systems. Every measurement can potentially tell scientists something about how other stars form planets, how icy bodies develop, and how material survives for billions of years between stars. And this is where the story becomes much bigger than one strange-looking object. Imagine finding a piece of rock or ice that formed around another star before our sun even existed. We would be examining material from a completely different cosmic history. Its chemistry, structure, and behavior could reveal. But the deeper scientists look into 3I, Atlas, the more important one fact becomes clear. This object cannot be studied like an ordinary comet. It came from outside our solar system, crossed an enormous distance between the stars, and is now moving through a completely different environment. That alone makes every observation valuable. One of the biggest questions concerns its movement. When a comet becomes active near the Sun, escaping gas and dust can produce a small amount of thrust. This is known as non-gravitational acceleration. Normally, scientists can use these effects to understand how material is leaving the surface. But when the observed acceleration does not perfectly match the expected amount of escaping material, researchers have to investigate further. There are several possible explanations. The object's jets may be stronger than estimated. Its surface may contain volatile materials that behave differently from familiar solar system comets. Or the measurements may change as additional observations improve the orbital calculation. This is why astronomers rarely make a major conclusion from one measurement. They collect observations over time. The longer 3I, ATLAS remains visible, the more accurately scientists can calculate its trajectory. And trajectory is extremely important. If an object is simply following a predictable path under the influence of the Sun's gravity, its future position can be calculated with impressive accuracy. But if additional forces are acting on it, the predicted and observed positions can slowly separate. That difference becomes a clue. Scientists can then ask what physical process could produce the extra acceleration. The dust surrounding the object provides another important clue. Dust is not simply decoration around a comet. It contains information about what is happening on the surface. The size of dust particles, the direction they travel, and the way they respond to sunlight can reveal how material is escaping. Large particles tend to behave differently from extremely fine dust. Gas molecules behave differently again. By studying these differences, astronomers can reconstruct the physical processes taking place around the nucleus. This is particularly important for an interstellar object because its chemistry may not match the chemistry of familiar comets. Different stars form planets under different conditions. The temperature, chemical composition, and distribution of material inside another planetary system could produce bodies with very different properties. So even if 3I, ATLAS eventually turns out to be completely natural, it could still challenge some of our assumptions. It may show that objects from other planetary systems can survive in forms we rarely see here. There is another fascinating possibility. The object may contain information about its original star system that has remained preserved for billions of years. Before the Sun formed, countless other stars were already being born, evolving, and dying. Planetary systems were developing around them. Asteroids and comets were forming. Some were eventually thrown out into interstellar space. A small number of those objects may spend billions of years traveling through the darkness between stars. Then, by chance, one enters another planetary system. And now we may be watching one of those ancient travelers. That makes 3I-ATLAS more than a passing object. It is potentially a natural sample of another planetary system. We cannot physically collect it and bring it into a laboratory. But telescopes can analyze its light. Spectrometers can study the wavelengths absorbed and emitted by its gases and dust. Spacecraft can observe its surroundings from different locations. Together, these measurements can reveal its composition. And composition may answer some of the biggest questions. What kind of material exists around other stars? Are interstellar comets chemically similar to those in our solar system? How different can planetary systems really be? And how common are these visitors? For decades, scientists suspected that interstellar objects should exist. But detecting one is extremely difficult. They move through enormous volumes of space, and most are incredibly faint. The fact that we have now identified an object from beyond our solar system means our ability to detect such visitors is improving. Future surveys may discover many more. Eventually, scientists could build an entire population of known interstellar objects. Then 3I-ATLAS would become one member of a much larger family. That would allow researchers to compare different objects and determine whether the unusual features seen here are truly unusual or simply common among interstellar visitors. This is where patience becomes important. The most exciting scientific discoveries do not always happen when the first image appears. Sometimes the real breakthrough comes months or years later, after researchers compare hundreds of measurements. An apparently mysterious feature may eventually receive a simple explanation. Or a small anomaly may survive every attempt to explain it. And that second possibility is where science becomes especially interesting. If an observation repeatedly refuses to fit existing models, scientists do not have to abandon physics. They improve the model. That has happened many